All right, class. So what we're going to talk about today is finding series that approximate the constant pi. And this is some bonus topics in our stint into Taylor series. And the way we're going to do this is first find a Taylor series that'll help us compute or come up with a bunch of infinite series that represent pi. And then we're going to use Google Sheets to try and figure out what the first 10 terms, first 20 terms of those series look like to give us approximations for pi. So right now we know pi is equal to 3.14159 and change, an infinite amount of change. But let's come up with some series that can give us that particular constant. And the series that we're going to first try to consider is a series for the arctangent. So if we can find a Taylor series for this the arctan, we're going to see how we're able to use that infinite series to give us approximations for pi by choosing clever x values. So let's get started. Let's first find the Taylor series for the arctangent. And of course, we're trying to come up with this power series representation for arctan. And we don't have we could do that whole kind of table method listing all the derivatives, seeing if we pick up on some patterns to write a compact series. But I'm going to draw our attention to the following idea. Now, we might not know what the arctangent is in terms of standard functions like sine, cosine, the exponential, etc. But we actually know something about the arctangent's derivative. The derivative of the arctangent is just equal to 1 over 1 plus x squared. So here's my idea. We're going to start off with this derivative relation. And then we're going to use fundamental theorem of calculus basically to integrate both sides. So let's actually just go ahead and throw on some integrals. Because on that right-hand or the left-hand side, the integral of our derivative by fundamental theorem of calculus, that's just going to give us back the original function. And on that right-hand side, well, we know how to write a power series or Taylor series for 1 over 1 plus x squared. So let's go ahead and do that. And this comes back to the idea of using our stencil for 1 over 1 minus some quantity. So if we go back to our stencil for 1 over 1 minus some quantity, inside those blue parentheses, well, here we just have minus x squared, and we know what series this is coming from. So we're still integrating the series. We haven't done that yet, but this is equal to the series from n equals 0 to infinity of just what's in those blue parentheses, the minus x squared, all raised to the nth power. So lo and behold, we're getting closer to a Taylor series representation for our arctangent. The last thing to do is really go ahead and integrate. Before we integrate, though, let's do a little bit of algebraic cleanup. So, well, we can swap the integral sign and the summation sign. And of course, there's some deeply rooted mathematical reasons why we're allowed to do this for these particular functions, which you might see in real analysis. And we can just do the algebra manipulation. So we have minus 1 to the n times an x to the 2n power. So last thing to do is just integrate the only x-dependent term in that series, which is the x to the 2n power. So if we go ahead and do that, what we're then left with is our infinite series from n equals 0 to infinity of minus 1 to the n times x to the 2n plus 1 power, coming from the antiderivative power rule, divided by 2n plus 1, plus a constant c. And at this point, you might be wondering, well, how do we know what the identity of that c is? Well, let's just evaluate the arctangent at x equals 0. Some value we know arctangent of. So if we evaluate the arctangent at x equals 0, well, every single term in that infinite series is going to be identically 0 because we're raising 0 to non-zero powers in general. So the only thing that's going to survive on that right-hand side is the c. Except we know the arctangent of 0 actually just in fact is 0. So c has to be 0 itself. So our Taylor series or power series representation for the arctangent happens to be this following infinite series from n equals 0 to infinity of minus 1 to the n of x to the 2n plus 1 all over 2n plus 1. And we're going to use this relationship basically to help us find a series formations or series representations of the number pi by choosing clever values of x. And the clever values of x we're going to choose are basically values of x in which we are given or we know the arctangent. So let's just jump right to that now. So number 2 that we'll do, evaluate at particular x values. And the first x value we can evaluate at is, well, x equals 1. And the reason we want to do that, we know the arctangent of 1 is equal to pi over 4. And well, now that we have that infinite series, we're just going to put x equals 1 into that infinite series. So we know that the arctangent of 1 written in the infinite series format is then just, well, a negative 1 to the n all over 2n plus 1. Because when x equals 1, we just have 1 to the 2n plus 1 power, and that's always going to give us a 1. So if we're looking for an approximation of pi, or a series that represents pi, all we need to do from the above line is solve for pi. So if we just multiply that series on the right by 4, we have our first series that represents pi. 4 times the infinite series from n equals 0 to infinity of negative 1 to the n all over 2n plus 1. So this will be one of the series that we investigate in a few moments. And again, this is a series when we let x equal 1 and we look at the arctangent of 1. So let's check out the next series. And this point might not be as obvious, but if we let x equal 1 over the square root of 3, what really helps here is knowing our unit circle values. We're investigating, well, the arctangent then of 1 over root 3. Which is actually equal to pi over 6. So when we plug in the value of x equals 1 over root 3 into that infinite series for the arctangent, we get minus 1 to the n. Now we get a 1 over root 3. And that's raised to the 2n plus 1 power. Now I'm running out of room. All over 2n plus 1. So if we were to solve this relationship between pi over 6 and this infinite series, we have another representation of pi that's equal to 6 times the infinite series from n equals 0 to infinity of minus 1 to the n of 1 over root 3 to the 2n plus 1 power all over 2n plus 1. And this is going to be the second series that represents the value of pi, and we're going to investigate both of these. And we're going to investigate both of these just using Google Sheets. So let's check it out. So the first case, when x equals 1, and we got our pi relationship of arctangent of 1. So if you remember, what we found for pi in this first case was pi is equal to 4 times the infinite series from 0 to infinity of -1 to the n all over 2n plus 1. So let's first try to compute this series in Google Sheets. And the way I'm going to try and orient this is we're going to make a list in Google Sheets of n, that's our counter. So n goes from 1, 2, or 0, 1, 2, 3, etc. And one feature of Google Sheets that's really nice is if we want to kick n further, we can highlight a pattern and then see this blue square on the right-hand corner of that highlighted region. We can pull it down. And in the next column, next to our n values, what we're going to do is basically try to write what the nth term of the series is. Just the nth term, not the sum of terms, just the nth term. So for example, in this case, if we go back to what we had for pi, an easier way to think about this might be if we actually take that 4 and bring it inside the series. So we have 4 times -1 to the n all over 2n plus 1. So this term that I'm going to circle in red, we're going to write that term in every single row in this column for different n values. So the way we can do this in Google Sheets is if we type an equal sign, we can start writing some math equations where we can start doing some calculations or write out just, functions times other things in that nature. So we can write 4 times -1, and we want to raise that -1 to the 0th power. And look at that counter next to us. That's what we want. So we can click on that counter that's in spot A6. And the next thing we want to do is divide by 2 times n plus 1. So we can divide, open parentheses, 2 times n. Well, n in this case is the value on the left-hand side. So we can click that box again. So we get 2 times A6 plus 1 end parenthesis. If we type enter, we get a value in that box. And what's nice is, well, this could be a very laborious thing to do if we had to write that formula in each and every row for every n value we cared about. But Google Sheets, or Microsoft Excel for that matter, are good on picking up on patterns. So if we just highlight that box and click on the lower right-hand side of that blue box, we can pull that down and it'll continue that pattern for us. So if we click on the next box, we can see, hey, this is 4 times -1 to the A7, which is the value of n to the left-hand side, divide by 2 times A7 plus 1. And you could do this for all those values. And well, if we actually want to start computing sums here of this infinite series, we can start computing partial sums. So the first partial sum is just the value of the first term of the series, which is just 4. The second partial sum is the sum of the 0th term and the first term. So we can do equals, well, the previous term, which is the spot above it, plus the next term, which is the value to the left, B7. If we click enter, that's the second partial sum. If we want the third partial sum, we can do equals, well, the partial sum before it, plus the next term in the series. So we can do plus, and then to the left, that value. And we could keep doing this. We look at the next partial sum is equal to the previous partial sum plus the next term, which is the term to the left. And well, what's nice about Google Sheets again, or Excel, is it picks up on patterns very nicely for us. So if we just highlight these boxes, click this blue box in the right-hand corner and drag it, we'll get those values. And well, we know the actual value of pi is 3.14159 and an infinite amount of change. And by the 18th partial sum of the series, or the 19th partial sum, we got 3.1 basically going for us. All right, the next thing we can do is, well, let's just completely pick on this pattern. So just choose maybe 4 or 5 rows, highlight those rows, and we're going to click this blue box on the right-hand side, and we're just going to drag this really far down. In fact, let's drag it as far as Google Sheets will let us. So going 200s, 300s, 400s. Basically, we want to see how many terms in this series do we need to actually get good approximations to pi. Oh, I got cut off at 1003. So I'll let go. Might take a couple seconds to load up. Oh, look. So by, I don't know, the 997th or 998th term in the series, we finally get 3.14. So we have the first 3 terms of pi correct. But again, everything we've done in this case, finding this pi series, if you will, using x equals 1 in the arctangent, we know that's going to converge to pi. But as you saw here, it took almost 1,000 terms, and we're only getting 3.14. We haven't even gotten any decimals beyond that. So let's go to the next pi series. And well, this was a series that we listed above. Let's just go ahead and use that. So this is when not x equals 1 now, but when we evaluate the arctangent at x equals 1 over the square root of 3. And when we go ahead and do that, that gave us arctangent of 1 over root 3, which was equal to pi over 6. So this was a series that we found directly above us. So if we write pi, we can do the same thing, pull that 6 inside of the series. So we have this as a series from n equals 0 to infinity of minus 1 to the n. Instead of just having a 1 to the 2n plus 1 power, we now have a 1 divided by square root of 3 to the 2n plus 1 power. I guess we need a factor of 6 from the factor of 6 there. So let's just stick that before the minus 1. And that's still divided by 2n plus 1. So for each term of the series, we're going to do the same thing. We're going to list a bunch of n's at first. 0, 1, 2, 3. Google Sheets or Excel will pick up on a pattern, so we can click, drag, get more terms of that pattern. And for each of these n values, we're just going to write what the nth term of that series is. Not the nth partial sum, just what the nth term is. So in this case, we have equals 6 times -1 for the counting variable, which is the value to the left. But instead of just 1, we have times 1 divided by the square root of 3, close parentheses. Parentheses are really important for computer programming. And we need to raise that to the 2 times n, which is n is the value to the left, E6 here, plus 1. We can end that parenthesis. And well, we're not done yet because we need to divide by 2n plus 1, that term in the denominator. So we have to divide, open parenthesis, 2 times the n counter, the value to the left, plus 1, and close parenthesis. Click enter. All right, we have some value for the 0th term. And this was a big equation we had to plug in here. Luckily, Excel, Google Sheets, good at patterns. Just highlight and drag. And the next thing we can do is start computing partial sums. So the first partial sum is just the first term of the series. So it's just equal to the value of the 0th term. The next partial sum is equal to, well, the previous partial sum value, the value above it, plus the next term of the series, which is to the left, and click enter. And we could keep doing that. The next partial sum's equal to, well, the value of the previous partial sum plus the next term in the series. And we could keep doing that manually, or we could highlight the 2 partial sum values we just put in based on the previous values, highlight and drag. And well, we're seeing something very special here, actually. It only took about 18 terms or even less, and we're picking up a lot of terms that are correct of pi. For example, by this 18th term, just highlight this 18th term for us. We're almost getting all the same values of pi. We have 1, 2, 3, 4, 5, 6, 7, 8 values of pi that look correct according to the true value of pi. So all this to say, we have a couple different series that represent what pi is equal to in an infinite series formation. Except some of those series converge to pi a lot faster. This second example, where we let x equal 1 over the square root of 3, we're getting 6 or 7 decimals of pi in only 18 terms of that series. Whereas the previous first example, where we let x equal 1, it took us almost 1,000 terms, and we're just getting 3.14. I also hope that this was a nice exercise in helping you use Google Sheets to compute infinite sums.